Hey guys, this is the physics notes on buoyancy. So this is part 3. In these notes, we're going to be talking about something that's submerged between two fluids. So it has a density that's somewhere in between, and what percentage of it is going to be above and what percent is going to be below that bottom fluid. So you should have already done the demo, but if not, make sure you go talk to your teacher about that. And we're going to get right into it. So let's go over negative buoyancy. So just remember, if an object sinks, its weight has to be more than the buoyant force. So if I have this cup of, let's just say it's water, and then I have this ball, and I take the ball and I release it. Initially, there's going to be a net force down. So I'm going to freeze it in this motion, meaning that the weight going down is greater than the buoyant force. So there's a net or overall difference in force, and that's in the downward direction. So it's going to accelerate down. Remember that whole F net or sum of all forces that we did before? So that's coming back. So while you're moving through the fluid, you know that the weight is greater than the buoyant force. It's still going to be greater than the buoyant force. The weight will be greater at the end, but we're going to have something else for an equation to bring later. All right, so the ball is going to continue going down until it hits the bottom of whatever the fluid it's going through. So like if this was a cup, until it hits the bottom of the cup. If this is a pool, until it hits the bottom of the pool. Then the weight is still the same. We still have that same downward force as the weight. We still have the same buoyant force, but it's no longer moving because we now also have the normal force, which is the contact force that the floor exerts up onto the ball. So when it hits the floor of the fluid, there's a normal force that the bottom of that acts on, and that's equal to its apparent weight. So we've got this. Buoyant force plus the normal force equals the weight once it's at the bottom. And this comes from the equation we did before, where we had the weight minus the apparent weight equals the buoyant force. So it's the same equation. So remember, the normal force is the weight apparent. So that's what the scale would say if you had a scale that read newtons at the bottom of the water. Okay, if an object just floats, it just hangs out in the fluid, whatever it is, then the sum of all forces is 0. So the weight is equal to the buoyant force. They're exactly the same. So buoyant force equals weight. Now, the buoyant force is also the density of the fluid times the volume of the object times gravity. And that equals the weight. So mass times gravity. So the mass of the object times gravity. So let's look at this equation for a second. When you have everything being multiplied by on either side, and you have a variable that's on both sides, then they can cancel. So gravity is gone. We've got a little bit of an easier equation to look at. The density of the fluid times the volume of the object equals the mass. Well, if we divide both sides by the volume of the object, just to make the left side a little easier, you'll notice the density of the fluid is equal to the mass of the object times the volume of the object. Well, if you have something equal to the mass of it divided by the volume, that's its density. So this only happens when the density of the fluid equals the density of the object. So when the density of the fluid and the density of the object are the same, it's neutrally buoyant and it doesn't float all the way up or sink. The funny thing about this is we still call it floating, and if something is positively buoyant, we call that floating too. So it's either sinking or floating. This floating scenario is when it stays in one up and down position. It's not going to go up or down. All right, so what if we have multiple fluids? So first thing I want to notice is the density on the top versus the density on the bottom. So these are the fluids. So this, let's say this is water and this is air. So the density of air is the top density, the density of water is the bottom density. So in this scenario, if our object is here or going down, we know that the density of the top is the smallest, and then either these two are equal or the object is more dense if it's sinking. That's one scenario. If this happens, where part of the object is above water, then we know that still the top fluid is going to be the smallest density, so the air in this case. The object, though, is somewhere in between the density of the bottom. So we're putting them right in order. The reason part of the object comes up is it's less dense than that bottom fluid, but it's more dense than the top fluid. So it's trying to sink under the top fluid while also being above the bottom fluid, and that's why it's going in between the two. And the last one, if something's up here and it's probably going up more, so the density of the object is equal, it could be equal to the density of the top fluid, or it could be less, because if it's going up, 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 and going eventually above, and that's less dense than the bottom fluid. So these are our three main scenarios. For today, though, we're mainly going to talk about the middle scenario, which I said earlier. So that's when something's floating in between the two fluids. All right, so if something's floating between the two fluids, first thing I want you to do on your notes is kind of draw this line through the object, and that's going to be our arbitrary line of where that bottom fluid comes up to. Now, it depends on the object and it depends on the densities, so this isn't always going to be at this point. You know, you don't always have a third above, but for today, that's just where we're going to draw it. Remember that you have the volume on the top. So any object has a total volume, or how much space it takes up. And if we just chopped off that top part, that is the volume on the top. Then we've got the volume on the bottom. So if we were to describe the volume in each fluid, as in submerged in each fluid, the volume on the top, so however much space this takes up, plus the volume on the bottom, equals the overall volume of the object, right? So like if you take an ice cube and you cut it in half, those two halves add up to the original ice cube. That's the idea. We also have a fraction of the object's volume. What do I mean by that? Okay, fraction on the top, as in the fraction of the object that's floating above, is going to be the volume on the top divided by the volume overall. So let's say that this whole thing was 4 meters cubed. If I have 1 cubic meter on top, then 1/4 of it is on the top, right? The fraction on the bottom is whatever the volume on the bottom is. Volume bottom divided by the whole thing. If this was 4 cubic meters and I had 1 cubic meter on top, I would have 3 on the bottom. So my fraction bottom would be 3/4. Now, when we use the fraction top, fraction bottom, you're going to probably use a decimal, so like 0.25, 0.42. So we can also convert those to percentages easily, because then you just move the decimal 2 spots. Keep in mind that the fraction on the top plus the fraction on the bottom is equal to 1, right? If you have 1/4 on the top and 3/4 on the bottom, those add up to 1. So if you have 0.15 on the bottom, you've got to have 0.85 on the top. So whatever you have on the bottom plus whatever piece of the object is on the top, they add up to be the whole thing. Now keep in mind, the reason this happens is because you're going to have a different buoyant force on the top than you have on the bottom, because they're two different densities. When you look at the formula for buoyancy, it's density of the fluid something's dissolved in times the volume of the object times gravity. So if you have different densities on top and bottom, then that buoyant force is going to pick up differently. No matter what, though, the weight's still the same, because that's the whole object. So the top buoyant force plus the bottom buoyant force equals the weight, because it's staying in one spot. You're not moving, you're not accelerating in either direction. So the upward forces have to equal the downward forces. Now, if we are substituting some stuff, remember the buoyant force is equal to the density of the fluid it's in, so this gas or liquid, whatever's out here, times the volume on the top only, because we're only talking about the top buoyant force, times gravity. This is the definition of what a buoyant force is. To define a buoyant force on the bottom, that'd be the density of the fluid on the bottom times the volume on the bottom times gravity equals weight, which is mass times gravity. You'll notice I didn't put mass times gravity. I did density of the object times volume of the object, because density times volume is mass. So density of an object times volume of an object is mass of the object. That's something from chemistry. You learned density is equal to mass over volume. So we're just bringing that back and plugging that in. That way this all looks kind of uniform. Now notice they all have gravity. If everybody has gravity on both sides of the equation, gone. Now it's already a little simpler. Now I want it to have just density of the object on one side, just to make things easy too. So if I do this, divide by volume of the object, I have to do that for every single term. Okay. These cancel on the right. Volume of the object is going to cancel. And now I know on my right-hand side over here, the only thing left is density of the object. So the right-hand side of my equation is just density of the object. Now let's go over and look at the left-hand side. Now if I look over here, you'll notice that I have volume of the top divided by volume of the bottom. And we saw that just a minute ago. Volume of the top divided by volume of the bottom, we labeled that as fraction top. So this technically is the density of the top fluid times just the fraction of the object that 0.12 or 0.75, whatever part of the whole object is up on the top. And then same thing here. Oops, sorry. The volume of the bottom divided by the volume of the object is the fraction of the bottom. All right, so here's your equation that works with the density of the object, how much the object is above a fluid, how much of it is below a fluid, and the densities of the two fluids it's in. Let's use that equation to solve some problems. All right, what percent of an ice cube would be above the water, assuming the air density is 1.29 kilograms per meter cubed, the density of the water is 1,000 kilograms per meter cubed, and the density of the ice is 917 kilograms per meter cubed. First thing I did is drew a picture, and I highly recommend when you do these problems, you draw a picture whenever possible and label things. It just keeps things straight in your head. All right, density of the air, so the top fluid is 1.29. Density of the water, the bottom fluid is 1,000, and the density of the ice is 917. Now notice I took out all my units in here. I just like working with just numbers as opposed to units. I think it makes things a little clearer. So let's plug stuff into our equation. What percent of the ice cube would be above water? So I want to know the fraction on the top. So it starts with density of the top fluid, 1.29, times fraction of the top. That's what I want to know. Plus density of the bottom fluid, 1,000, times the fraction of the bottom, equals density of the object. The object we're talking about here is ice, so equals 917. All right, so I want to know the fraction on the top, but I have two variables, and you can't solve a problem with two variables. So we have to bring about this equation again that we had before. Remember the fraction of the top plus the fraction of the bottom equals 1, right? So fraction of the top's cool. We don't want to change that in the equation. But the next thing, fraction of the bottom, I got to get rid of that. So I'm going to do a little math, and I'm going to substitute in. So if I take away fraction of the top, so I solve for fraction of the bottom, that equals 1 minus ft. So I'm going to use that here instead of fb. Whichever one you're trying to get rid of, whether it's fraction top or fraction bottom, substitute it with 1 minus the thing you want, because they add up to 1. So this is still 1,000, but now instead of fb, I'm doing 1 minus ft, because that's the same thing as fb. And it still equals 917. All right, I'm going to need to keep this the same, but then distribute my 1,000 into both of these. So 1 times 1,000 is 1,000, and then 1,000 times negative ft, don't forget your negative sign, is negative 1,000 ft, equals 917. All right, I'm not doing anything else inside these parentheses here, so I can not worry about them, and I can add up like terms. So I've got negative 998.71 ft plus 1,000 equals 917. Let me move this little window here. We're going to minus 1,000 from both sides. So this is still negative 998.71 ft, and now this equals negative 83. I want ft by itself, so it's currently being multiplied by negative 998.71. So I have to divide by that to get rid of it. Do it on both sides. My fraction on the top is 0.083. I'm going to convert that to percentages. So 8.3% of the ice cube is going to be floating above water. Okay, here's another one. So for this one, what if there was oil above the water instead of ice? And oil has a density of 800 kilograms per meter cube. So let's bring in those variables. I'm going to give you the answer, and you're actually going to solve it on your own. So you're redoing a very similar problem, but now there's no air on top. So if you have a denser fluid than air, how much of it is there? And you'll notice it's bigger percent on top because a denser fluid has a larger buoyant force. So oil is able to push up on the ice more than air is. But I want you to do the math and make sure you get that answer. If you don't, talk to your teacher, and I will see you in the next set of notes. All right, thanks.